The first one is by anybody's standards, especially by Rob's standards, not a real single case design, or not one that would get approval by anybody. It's a single phase study, only treatment. When I see that there's only one phase, I always think there is an implicit baseline phase that we don't see, that they didn't measure. This was a weight loss study. So you know these people, before they got in that weight loss study, knew what their weight was before that for some period of time, and it was probably either steady or on the increase. It wasn't going down already. So you know what the baseline was, but in a scientific sense, you don't know anything about it. Subjects were 8 women. Starting weights ranged from 170 to 222. So they trained in self-control techniques, and their weight was recorded monthly for a year. So here is what their behavior, no, it's not behavior, it's what their weight looked like over that period. If you stare at these a long time, you'll see a couple of things. Of course, a strong downward trend. It looks fairly linear, except there are a few cases where it looks like there's a kind of a curve. There's a little ski slope in it. You know, it's not quite looking straight. Especially, patient 1, for example, takes a steep drop and then still declines, but maybe not at quite the same rate. So already there were some possible issues there. I wanted something that was nice straight lines, but this may not quite fit the bill. So, and then you see some people lost at a very high rate, like this first patient. Some people lost at a slower rate, like this second patient appears to be. Although it's hard to compare across patients. You see why it's hard to compare across patients? Because these people have different scales for different graphs. This goes from 180 to 225. This goes from 135 to 180. So it's a little hard, but you get the idea that there may be, it's fairly straight. There may be a little curve in it. There may be differences in rates of weight loss for the people, and we want to model all these things. Okay. Well, there are a lot of things that go wrong, but they're mostly technical things, so I won't describe them unless I have to. If any of you are, I'll now talk to the methodologists. If you want to analyze data, but they're only published in the form of graphs, like these data, and you don't have the actual numbers, there are programs that you can make copies and follow the line down, trace the line, and it will generate the actual data points for you in an SPSS file. So there must be something better now, but there was a program called Ungraph that we used about 10, 12 years ago. We used this to read this data and translate it into numbers. So if you're interested in reverse engineering data to analyze it, you can do it. All right, let me explain what this equation, or this series of equations, tells you. It only looks complicated because it's got Greek letters in it. It says, basically, I want to predict the number of pounds a person J weighs at a particular time I by an intercept plus a slope times the number of months into the study they were. But I didn't just use months. I subtracted 12 from months. That may sound strange. I wanted to model so that this intercept represented their weight at the end of the study, not at the beginning of the study. I don't want to model what they are at the beginning of the study. I know what they are at the beginning, and it's not affected by treatment. I want to know what it is at the model, what it is at the end of the study. And if you remember in regression, the intercept represents the prediction of your dependent variable, pounds, for when the independent variable is 0. So when months minus 12 is 0, when is months minus 12 equal to 0? When months equals 12. So if you put a 12 in here, 12 minus 12 is 0. That cancels that out. This is the prediction for 12 months. So that the other values of this are it's 0, minus 1, minus 2, minus 3, going back to the beginning of the study, is how many months you are before the end of the treatment. Okay. So, I see this didn't translate well into PDF, but anyway, if you look at this, you've got an intercept for each person and a slope for each person. This is modeling each person as a straight line. So a straight line has an intercept and it has a slope. The slope is how fast they're losing weight, which is one of the things we're mainly interested in. The intercept is where they ended. So in this model, there was nothing predicting differences among people in their slopes, and there was nothing in the model predicting differences in their intercepts. We just had a beta term for what the average was at the end and what the average rate loss was, weight loss. And here's part of the results. If you look at here, the average ending weight was 156 pounds. We don't care too much about that. What we care about is this, the slope. The average slope was minus 3. That means they lost an average of 3 pounds a month. Okay? So the average ending weight is 156. The average rate of loss is 3 pounds a month. But did they differ among each other? Were there differences among the people? That we have to look to. I'm going to make the model more complicated here to see if let's see if the explanation is any better when you put in a squared term. If you allow for not a straight line but a curved line, does that make things better? Because those lines didn't look straight, so we wanted to test that. And the interesting thing is down at the bottom where, and it's harder to interpret these numbers, but the fact is that this is significant, that the quadratic effect is significant, meaning there was an average a curvature in these lines. So we couldn't take them as just straight lines. Even though it was really tiny, it wasn't much of a curvature, it was enough to detect. And this summarizes visually what I did. Here's the raw data in the upper left with all the curves on one axis, so you can more easily compare the different people, some of whom lost at a slower rate, some of whom lost at a greater rate. Here's what the straight line model would predict for that to look like. So compare this with the actual data and see if that impresses you as being very similar. Now compare this with down here at the bottom, the quadratic model. Slight, you can tell visually, there's a slight curvature in this, but it's significant. And so statistically, it fits better. And to me, of course, it's subjective, right? And I'm the one looking at it, but hopefully to you too. This one looks like a better fit to these actual data than the linear one on the right. So what does that mean? It means that patients lost weight at a faster rate at the beginning, and then they tend to slow down at the end of treatment. So there's a very slight curve, but it's detectable. Now, did this study establish that the treatment was the cause of the weight loss, according to Rob's standards? No? You got 12 curves, but that's a lot of data, but it didn't have any change in treatment. It was all treatment, no control. But a nice statistical exercise for analysis. Now we go to one that's slightly more complicated. This one has two phases. It's a multiple baseline design. So everybody's got an A and a B phase. We've got the dependent variable is the frequency of pretend play actions in a 10-minute observational interval. So frequency of play actions, it could be anywhere from 0 on up. And you know you've got problems with this. You can't use an ordinary analysis assuming normality, because something that's 0 has no variability. It can't go down further. Only when it's positive can you, if you had a mean of 0, there's no variability. As you go up, you get more variability with bigger counts. So you need a different kind of analysis for this. The subjects are 5 toddlers. Their ages are pretty constant, 27 to 29 months old. But their level of, they had varying degrees of disabilities. They had cognitive functioning ranging from 14 months to 22 months. Okay? So all of them below what you would hope for, but some by more than others. And the treatment was a responsive teaching program with prompting and praising for the target behavior. So now we have, the measurement is counts. How many pretend play behaviors occurred in each 10-minute interval. And here is the graph. This is pretty good. You've got, during baseline phase, you got something which almost never occurs. For these people, never occurs in this one, and almost never. And you've got a big, what appears to be a nice response here for these two, for this one. Here it's not so certain whether anything's happening or not. Okay, so visually you see what's going on. I guess my hand is so visually you can see what's going on. Can you quantify it? And can you explain any differences in what's happening among the 5 kids? Okay. So for the people with some technical knowledge, we used a Poisson model. For those of you without any technical knowledge, we used a Poisson model. We used a fish model, right? Poisson, Mr. Poisson was a mathematician. His name is Fish, right? So each session lasted the same amount of time, but we could handle, as the technical people know, we could handle it if session times vary, which sometimes they do. Sometimes you have longer sessions, sometimes shorter sessions. You can just do a model for rates. for that. The Poisson has the interesting quality here that we needed, which is there's a larger variance for a larger mean. If you have a mean of one observation, one pretend play action per session, if people are going on with one, they're not going to go very high. They'd go 0 or 1 or 2, 1, 0. It'd be small values, and there wouldn't be much variability in it. Whereas if they're averaging 5, it'd be 5 and 4 and 7 and 3, a lot more variability for a 5 average. So the Poisson does that trick for us, handles the heterogeneity of variance. Yeah, we don't care about that. Don't care about that. Okay. So there's a